Today we're going to be looking at section 6.3, sampling distributions and estimators. Okay, so we want to talk about and learn about a sampling distribution. So what this is basically going to tell us is that we're going to be working with samples instead of the entire population. And really in statistics, that's what we do most of the time because a population is going to be so large that we aren't going to be able to work with the original population itself. We're going to work with samples that are drawn from that population. But the whole idea only works if we know that that sample is representative of the population and that the characteristics that we find for that sample are going to be true for the population. So we're going to look at different sampling distributions of a statistic. So some of these are going to be a sampling distribution of a sample proportion. We're going to also look at a sampling distribution of a sample mean. So what this is, it's a distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. So I'm going to kind of be demonstrating that over the course of this section. So we can represent these in different formats, the probability histogram, the formula, or the table. We're going to mostly be doing the table here in this section, but just understand that they can be represented in other ways. Okay, so to get started talking about the sampling distribution of a proportion, we need to introduce some notation here. The lowercase p in this situation is going to represent our population proportion, and the p hat, which is how this is read, p hat, is going to be your sample proportion. So just keep those in mind as we go through this. Okay, so with a sampling distribution, what we're going to do is we're going to go in and we're going to randomly select n values. So we're going to pick a certain number of values, and then for each sample that we gather, we're going to find the proportion for that sample. And we're going to record those proportions for a lot of different samples. So we're going to take a bunch of different samples, and for each sample, we're going to record the proportion for that sample. And then when we plot those proportion values, what happens is that sample is going to tend to have a normal distribution. Okay, so regardless of what we started out with here, when we take all those samples of a given size and take the proportion for each of the samples and plot those proportions, we end up with a normal distribution. Okay, so as far as the behavior of a sample proportion, there's two characteristics that I want you to know. The first one is that a distribution of sample proportions tends to approximate a normal distribution. And that's what we just demonstrated or just looked at here, is that it tends to have a normal distribution. The second is that the sample proportions target the value of the population proportion. So basically by studying the sample proportion, we're able to learn information about the population proportion because it does estimate that. Okay, so it does target the value of the population proportion in the sense that the mean of all the sample proportions p hat is equal to the population proportion p. So the expected value of the sample proportion is equal to the population proportion. So this is what's called an unbiased estimator. So p hat is an unbiased estimator of p because it doesn't introduce any kind of bias into it. And that's what we want to work with, is we want to work with unbiased estimators. Okay, I have a little demonstration that I want to show you here. So we talked about proportions and sampling distributions of proportions. What I want to demonstrate here with this simulation, and you can go to this site and play around with it a little bit if you would like as well, and that is if we start with a normal distribution. So this is our parent population that we're going to draw our samples from. We want to select samples of a given size. And in this case, we're going to be working with samples of size 5. So I'm going to draw 5 samples. And so what happens is you saw that from this population, we selected 5 different values, and then the mean of those 5 values was plotted on this graph here. So if I do that again, okay, I get a different mean if I do it again. Okay, so I could keep doing that, but this allows me to kind of generate this in large numbers. So if I do this 10,000 times, then it's not going to show me the animation of it all, but you can see that what happened is the distribution of the sample means is also a normal distribution. So I could fit a normal curve to that, and you can see it's very much the same. I could also look up here and see that the mean of this one is all of my parent graph is also the mean of this distribution here. If I wanted to compare this and look at the mean, and this time let's look at a little bit larger sample here. Okay, so if I'm going to choose, when I'm choosing a sample of size 5, I can see that I still have this normal distribution. And if I choose a sample of size 25, I also have a normal distribution. What you notice is that as my sample size gets larger, the variation in the values gets less. Okay, so this is a lot more clustered here near the mean, whereas this one's a little bit more spread out. And that's something we'll look at with the central limit theorem in section 6.4, but that's an important concept there. If we look at some of these others, let's look at the variance. Okay, what you'll notice with the variance is that and let me switch this one to variance as well. Okay, so if we're looking at the variance, our variance is actually skewed to the right when you look at the variance, the distribution of the variances. But as your sample size gets larger, it does tend more to be a normal distribution, but it has the characteristic of being skewed to the right with that. I'm going to go back and look at the means here for just a minute because I want to show you that it really does not matter whether a population is normally distributed or not for these characteristics to be true. Because if we look at, let's say, a uniform distribution and we pull samples from it, I want you to see what happens with that. When we pull samples from a uniform distribution, our distribution of sample means still tends to be normally distributed. And you can see that here with even a larger sample size. If I look at a skewed distribution, something here that's skewed to the right, and I plot those, then here I see that I have a distribution that is normally distributed in each of these cases. So even though my parent population was not normally distributed, the distribution of the means is going to be normally distributed. And I can even make up some kind of weird custom population here, something that looks like this, and plot the points, and I still end up with a normal distribution. So this is just kind of showing you that regardless of what the original parent population is, and when I plot the distribution of the means, I'm going to get a normal distribution. So this is just a slide showing basically what we went through with the simulation. We selected n values and found the sample mean for each sample. We record those sample means and then we plot these and we see that it does give us that normal distribution. So to summarize this, the distribution of sample means tends to be a normal distribution, okay? So regardless of whether we start with that, the distribution of sample means tends to be normal. And the distribution tends to become closer to a normal distribution as the sample size increases. Okay, the sample mean targets the value of the population mean. So our notation for sample mean is x bar. That targets the population mean, which is mu. So what that means is the mean of the sample means is the same as the population mean. So they are equal to each other. The mean of the sample mean and the mean of the population mean are going to be the same. Okay, looking at variances, if we go through the same process where we randomly select n values and then find the variance for each sample, what we'll find is that if we list all of our samples, if we plot these as you saw in that demonstration, variances tend to be right skewed with that. So the distribution of sample variances tends to be a distribution that's skewed to the right, and sample variances target the value of the population variance. So sample variance targets the value of the population variance. And basically what that says is that the mean of the sample variances is the value of the population variance. And the reason this is important is because very rarely do we have that population to work with. So if we know that by finding the mean of the sample variances and knowing that it's going to be the same as the mean of the population variance, then that is very valuable information for being able to study these and draw conclusions from them. Okay, so some of the homework that you're going to have on MyStatLab is going to have you go through problems like this. So I want to do a couple examples here. So this one's looking at the sampling distribution of the sample mean. So here it says the assets, and these are in billions, of the 4 wealthiest people in a particular country are listed here. Assume that samples of size n equals 2 are randomly selected with replacement from this population of 4 values. So the first step here we want to do is to list all samples of size n equals 2. So to save on time, I just went ahead and wrote these out. But if we want to list all samples from this population of size n equals 2, we just want to keep ourselves organized. So if I'm going to pick 2 from here, let's just say I'm going to pick 47. So my first one might be 47 and my second one might be 30. Then I might have 47 and 19, 47 and 18. And since we're doing this with replacement, I could even have 47 and 47. And then if I move on, if I pick 30 the first time, then I might have 47, 30 and 30, 30 and 19, 30 and 18. And then moving on from there, 19 and 47, 1930, 1919, and 1918, and so forth. So what you'll see is that I'm going to have 16 different samples that are possible if I'm looking at samples of size n equals 2. There's a reason that our population is very small here and that we're choosing small samples, because you can see that even with a population of size 4 and samples of size 2, we get 16 different possible samples that we need to consider for this. So these are all the possible samples of size 2 that can be pulled from this population here. Okay, part B on this says find the mean of each sample and construct a table representing the sampling distribution of the sample means. So this is the table that we just came up with where we listed all of our samples. So since we're doing the sampling distribution of the sample mean, we're going to take each one of these small samples and we're going to find its mean. Okay, so 47 plus 30 divided by 2 gives us 38.5. So that's where we're getting this value. So we're going to do that for each one of these, and we're going to write all those down in this column here. Okay, we're going to construct a table to represent this sampling distribution. So what we want to do is we want to list all the possible X bars. Okay, so if I look at these, I want to kind of keep it organized and keep it in order. So I see that I have an 18, I have an 18.5, I have a 19, I have a 24, I have a 30, a 32.5, a 33, a 38.5, and a 47. So just kind of organize them. And this list should list everything that's here, but don't list it twice. Just list it one time. Then we're going to go back and assign the probability for each one. Okay, so to construct our probability distribution, I want to look and see how many 18s I have. So I have 1 18, and out of that, that's out of 16 total. So if I look at the 18.5s, I have 2 of those, so 2 out of 16. On the 19s, I have 1. On the 24s, I've got 1, 2. The 24.5s, I've got 1 and 2. The 30s, I've just got 1 of those. The 32.5s, I've got 1 here and 1 here, so 2 of those. The 33s, I've got 2 of those. The 38.5, I've got 2 of those. And the 47, I've just got 1 of those. So I want to make sure that these add up to 16. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have a total, if I were to add this up, of 16 over 16, which is going to equal 1. So this is going to be my probability distribution to represent the sampling means that I have here. Okay, so moving on to part C, compare the means of the population to the mean of the sampling means of to the mean of the sampling distribution of the sample means. So first of all, we want to find the mean of the population. So our population are these 4 values here, the 47, 30, 19, and 18. So to find the mean of anything like that, we're just going to add them all up and divide by the total. So if I add those values up and divide by 4, because we have 4 values, then I get 28.5. Okay, so we want to compare that to the mean of the sampling distribution of sample means. So I'm going to go back, and if I look at the mean here of my sample means, so I want to add all of these values up. So I get this 456 when I do that. So I'm going to do 456 divided by 16, which is what I had, and that's going to give me the 28.5. You notice these two are equal to each other, and that's what we would expect. So the mean of the population, okay, so the mean of the population, mu, is equal to the mean of the sample means. Okay, do the sample means target the value of the population mean? In general, do sample means make good estimates of the population mean? So the sample means target the population mean. In general, sample means do make good estimates of population means because the mean is an unbiased estimator. Okay, so moving on to an example of a sampling distribution of the sample proportion. So here we have a sample of size 3. So we're going to find all possible samples of size 2. So our population has 3 in it. We're going to find all samples of size 2. So if we go through and mix and match every one of the different values in the population, doing this with replacement, then we see that we have 9 different samples total that we could draw of size n equals 2. Okay, part B, construct a probability distribution table that describes the sampling distribution of the proportion of odd numbers when samples of size n equals 2 are randomly selected. Okay, so we're going to look at each one of our samples, and we're asked to look at the proportion of odd numbers. So if I look at this sample, neither of those are odd numbers. So I'm going to have 0 out of 9, which would just be 0. If I look at this sample, one of the two, sorry, let me back up. That would be 0 out of 2, not 0 out of 9. So here, looking at this, I have 2 values in my sample. I have one odd and one even. So I've got the probability of an odd is going to be 1 out of 2. So if I look here, both of these are even, so my proportion is 0. If I look here, 1 is odd, so its a proportion is 1/2. Here, both are odd, so my proportion is going to be 1. I have one that's odd, so it's going to be 1/2. None are odd, so it's 0. One's odd, so it's 1/2. And none are odd here, so this is going to be 0. So when I look at making my probability distribution, the sample proportions that show up are 0, 1/2, and 1. And that's why I list these here. So when I go back and look at how often they're occurring, I've got 1, 2, 3, 4 zeros. So that's why it's 4/9. And then I've got 1, 2, 3, 4 1/2, so 4/9 again. But I've got only one case that has a 1, so that gives me a probability here of 1/9. Okay, so moving on, part C, does the mean of the sample proportions equal the proportion of odd numbers in the population? So let's look at the population first of all. Here's our population. So the proportion of odd numbers here in this population is 1 out of 3, so 1/3. If I look at the p hat, I'm going to go back here. Okay. So if I add up the proportions of the p hat, so if I add these values up, I've got 3. So 3 out of a total of 9 is going to be 1/3. So again, these two equal each other because p hat is an unbiased estimator of p. So do the sample proportions target the value of the population proportion? Yes, it does because it is an unbiased estimator. Okay, looking at one more example here. On this one, the ages of 3 government officials when they died in office are given. complete parts A through D. So assume that 2 of the ages are randomly selected with replacement. List the different possible samples. Okay, so looking at these three values from the population, if we look at all of those samples, then this is our list that we would have for those different possible samples. Okay, so on each of these, we're going to look at the range for this one. So if I look at the range for each sample, the range we know is the maximum minus the minimum. So there is no difference here, so the range would be 0. Here it would be 9, 7, 9, and so forth. So when we write our probability distribution, our range is either a 0, a 7, a 9, or a 16. And the probability of each one of those is, if we look at the zeros, we've got 1, 2, 3, so 3/9. We've got 2 7s, we've got 2 9s, and we've got 2 16s. So if we add these up, we get 9 out of 9. Okay, so compare the population range to the mean of the sample ranges. Okay, so if we go back and we look at our values here, if we consider the range here, we're going to be subtracting 61 minus 45. So 61 minus 45 is going to give us a range of 16. If I look at the mean of the sample ranges, okay, if I add all these ranges up, I get 64. So the mean of that is going to be 64 divided by 9. And you can see that these don't equal each other because the range is not an unbiased estimator. So not everything is a good unbiased estimator. And as we go on and build in chapters 7, 8, 9, and so forth, we're going to see that we construct most of the techniques that we use in statistics around these unbiased estimators. So it's really important to know which ones are unbiased and understand why they are. So an estimator is a statistic that's used to infer or estimate the value of the population parameter. So this gives us the ability to work with a sample and know that whatever we find about the sample is going to be true for that population. So an unbiased estimator is a statistic that targets the value of a corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that's equal to the corresponding population parameter. Okay, so the three unbiased estimators that we're going to be working with are the p-hat for proportion, x-bar for mean, and s-squared for variance. So it's important to know each one of those and also to know what they target. So some of the biased estimators that we were not really going to work with, we saw that range did not work well. Median also doesn't work well. Standard deviation actually introduces a small bias, and so sometimes we do work with standard deviation, but in general is considered to be a biased estimator. Okay, so why did we sample with replacement? There's a couple of reasons for this. When we have a relatively small sample coming from a large population, it goes back to that 5% rule. So that we looked at in chapter 4, it basically makes no significant difference whether we sample with replacement or without replacement. So the other reason is that when we're working with independent events, it does make the events easier to analyze and result in simpler calculations and formulas. Okay, so to conclude here, we've got our list of our unbiased estimators and our biased estimators. So here the mean x bar targets the population mean mu. The variance, which is s squared, targets the population variance, which is sigma squared. And the population proportion is targeted by the p-hat, which is the sample proportion. So when we say it targets, that's another way of saying that it's equivalent to that. Okay, that takes us through this section. This section is much more conceptual and not as many calculations, but it is very fundamental to the sections that'll be coming up. So it's really important that you do understand these concepts.